Okay, welcome to our third tutorial for SPPH 400. In this tutorial, we're going to first have a quick review of the concepts of the sampling distribution and the central limit theorem to introduce the idea of the 95% confidence interval. We're then going to talk about why we must replace Z with T when we're doing statistical inference. We'll also talk about confidence intervals, including their assumptions and how we calculate these, as well as the underlying logic around the construction of a confidence interval. We'll go over what the margin of error is and how this can be controlled by using an appropriate sample size. And we'll conclude by discussing the difference between one- and two-sided confidence intervals. So before beginning our discussion on statistical inference, let's remind ourselves of the idea of a sampling distribution and the central limit theorem that we've talked about in the last couple of tutorials. So let's say we took numerous samples, calculated sample means for each of those samples, and then plotted those means. This is what's called the sampling distribution of the sample mean. It describes the distribution of all possible sample means that we may get when we take a sample. When we collect a sample, our sample mean is one of many we could get. We expect our sample mean to equal the true mean, but we know that it will probably not be exactly the same as the true mean. It'll probably vary from this a bit. The central limit theorem tells us that under certain conditions, our sample mean varies according to the normal distribution. So these conditions are that the observations were independently and randomly selected, and that there's a large sample size, or that the observations come from a normally distributed population. If we know our true mean, we use the concept of the standard deviation of the sample mean. And this tells us, on average, how far the sample mean will move from the true mean. If we don't know the true mean, we use the concept of the standard error, which is only based on the information we have in our sample. The standard error gives an idea of how far the sample mean varies from the true mean on average. So it's used to describe the accuracy of our sample mean as an estimate of the population mean, or an estimate of how close our sample mean is to the population mean. We know that 95% of all possible sample means are within approximately 2 standard deviations of the true mean. So in other words, if we reach out 2 standard deviations on each side of the true mean, 95% of all possible sample means will be within this interval. So 95% of the time, we'll get a sample mean that is within 2 standard deviations of the true mean. And we can also say that 95% of the time, the true mean will be within 2 standard deviations of our sample mean. So far in the course, we've mostly focused on how samples behave when we know the truth for the entire population. For example, if we know the probability distribution, mean, and variance of the population for a random variable, then what is the probability of observing certain things when we take a sample of data? And this is when we use Z-scores. A Z-score is a standardized score used when the population standard deviation is known. When we take a sample of data and calculate a sample mean, a Z-score tells us how many standard deviations our sample mean is from the true mean. And as we discussed in previous tutorials, Z-scores follow a normal distribution. And they're calculated by subtracting our sample mean from the true mean and dividing by the standard deviation of the sample mean. With statistics, we are usually looking at things from the opposite direction. So rather than starting with the truth of a population, we usually start with our sample and are trying to learn about the population based on our sample. So the question then becomes, given what we saw in our sample, what do we think the truth may be for the larger population? This is the case when we would use a t-statistic rather than a z-statistic. In this situation, we're only using the information we have available to us in our sample. We don't know the true value of the standard deviation, so we use the sample standard deviation as an estimate of this. A t-score is calculated in the same way as a z-score, except that we use the sample standard deviation in our formula rather than the true standard deviation. And compared to a z-score, which follows a normal distribution, a t-statistic follows what's known as a t-distribution. So what's the difference between a z distribution and a t distribution? Essentially, the t-distribution accounts for some extra uncertainty introduced by using the sample standard deviation rather than the true standard deviation. The sample standard deviation is a random variable. It is not a constant like the true standard deviation of a variable. We know that the value of the sample standard deviation will change for different samples of data. So we must factor in this extra uncertainty in estimating the standard deviation as well. So the t-distribution is like the normal distribution, except that it accounts for the extra uncertainty associated with having to estimate the standard deviation. It's bell-shaped and symmetric about its mean, except that the tails are a little bit thicker than a normal distribution. So the t-distribution is sort of like the normal distribution for samples of data. The larger the sample size gets, the closer the t-distribution gets to approximating a z or normal distribution, and the closer our estimate of the standard deviation gets to the true standard deviation. Let's take a look at the t-distribution with different degrees of freedom and compare it to the normal distribution. You'll notice that as the degrees of freedom, so pretty much the sample size, gets larger, the t-distribution converges towards the standard normal distribution. With the degrees of freedom of infinity, which is basically a sample size of infinity, the t-distribution actually is the normal distribution. For example, for z, the area between negative 1.96 and positive 1.96 standard deviations is 95%. There is 2.5% in each tail past a z-score of positive and negative 1.96. For a t-distribution of an infinite sample size, the area between plus and minus 1.96 standard deviations is also 95%. And even a sample size of 121, or a degrees of freedom of 120, is pretty close to that. So now let's try to make connections between some of the concepts that we've learned so far to introduce confidence intervals. So let's say we're interested in making inferences based on our sample data about a population's mean. We know that our sample mean is our best guess at the true mean. We also know that because of sampling variability, our sample mean is probably not exactly equal to the true mean. So we can make an interval that we are, for example, 95% sure that the true mean is in. This is called a confidence interval. The most commonly used value for a confidence interval is 95%. There are three main assumptions for confidence intervals. We assume that our sample was an unbiased simple random sample, that participants were obtained randomly. We assume that the values of observations derived from our sample are independent, so the inclusion of one participant does not affect the likelihood of another participant being included in the sample. And we assume that the observations of the sample that we are taking come from a normal distribution, or that the sample size is large enough to apply the central limit theorem, that the sample mean is at least approximately normally distributed. So essentially, this is saying that either the distribution we sample from must be pretty symmetric, or our sample size must be large, so greater than 20 if the distribution is not very skewed as a guideline. So this is the general formula for confidence intervals, and it might look a little bit complicated at first glance, but it's actually quite simple when you break it down. So the formula of a confidence interval is generally the form of an estimate, such as our sample mean, plus or minus a margin of error. And this is equivalent to saying the sample statistic plus or minus the t or z value times the standard error of the sample statistic. The first part of the blue box is our t or z value. Usually we're interested in 95% confidence intervals, so this corresponds to an alpha or significance level of 5%. We divide this alpha by 2 to get 2.5%, since there's 2.5% in each of the tails of the distribution. So if we don't know the true population standard deviation and are only working with the information that we have in our sample, we'd be interested in the t-score associated with 2.5% in the tails. The value of this t-score will depend on our degrees of freedom, which is defined as our sample size minus 1. So based on our sample size and the level of confidence we're interested in, we use a t-table to determine our t-value. If we wanted to calculate a 95% confidence interval and had a sample size of infinity, this would be a t-score of 1.96. This is the same value that we would use for a z-score if we knew the true population mean and wanted to calculate a 95% confidence interval for sample means. But if we had a sample size of approximately 101 to 121, this would correspond to a t-statistic of approximately 1.98. So as I said, our confidence interval is usually our sample statistic plus and minus our margin of error, with the margin of error meaning the t or z value times the standard error of the sample statistic. If our true mean and standard deviation are known, we use a z value. For example, 1.96 if we're interested in 95% confidence intervals. So our equation is the true mean plus or minus 1.96 times the standard deviation of the mean. And our interpretation is we are 95% confident that we will get a sample mean that is between the confidence interval. Notice here that our interpretation is focused on the sample mean since we know what the true mean is. If the mean is unknown, but the standard deviation is known, this is our formula. It uses the sample mean, a z-score, and the true standard deviation. This is a textbook case. It's extremely rare that you would know the true standard deviation and not the sample mean. But in this case, our interpretation would be we are 95% confident that the confidence interval will capture the true mean. When both the true mean and the true standard deviation are unknown, which is most often the case, we use the sample mean and the sample standard deviation and a t value rather than a z value in our confidence interval calculations. And the interpretation is we are 95% confident that the confidence interval will capture the true mean. Remember though that the true mean is a fixed value. It's not a random variable. So in your assignments and exams, do not interpret confidence intervals as there is a 95% chance that the true mean is within the confidence interval. Instead, say that you're 95% confident that the confidence interval will capture the true mean. What's the difference? The population mean has one value. You don't know what it is, but it has one value. If you repeated your experiment, that true value wouldn't change, and you still wouldn't know what it is. So therefore, it isn't strictly correct to ask about the chance that the population mean lies within a certain range. In contrast, the confidence interval you compute based on your sample depends on the data you happen to collect. If you repeated the experiment and got a new sample, your confidence interval would almost certainly be different. So you should make a statement about how confident you are that the confidence interval contains the population mean. So the main difference is that your level of confidence is about the interval capturing the true mean rather than about the chance of the true mean being within the confidence interval. It's a subtle distinction, but it's an important one. I just want to briefly discuss the margin of error, which I mentioned is a critical part of our confidence interval formula. The margin of error tells us the maximum expected difference between the true population parameter and the sample estimate of that parameter. So for example, the true population mean and a sample estimate of that mean. The larger our margin of error, the less confidence we have that our sample estimates are close to the true values. So the margin of error is dependent on three things: the t we use, so the level of confidence, the sample standard deviation, and the sample size. We'd like this interval to be as narrow as possible in order to get closer to the true mean, to be more confident in our estimate of the true mean. So if we wanted to decrease the margin of error and thereby decrease our confidence interval, we can do three things. We can use a smaller value of t, which means we lower the level of confidence by using a higher alpha. We can reduce the sample standard deviation, or we can increase the sample size. Decreasing the level of confidence is not a good option, as we'll be less confident that our interval contains the true mean. And decreasing the sample standard deviation is very difficult, if not impossible. So the sample size is the thing that we have the most control over. So the main thing we can do to decrease our margin of error and our confidence intervals is to increase our sample size. So let's try an example problem. Suppose 150 college students were asked their IQ. From the data, you find that the sample mean equals 120 and the sample standard deviation equals 11.3. What is the margin of error associated with a 95% confidence interval? What is the 95% confidence interval, and how do you interpret it? Since our sample size is large, the t-distribution approximates a normal distribution, and we can use a t-value of 1.96. As you'll recall from our t-table, a t-score of 1.96 gives us 2.5% in each tail of our distribution, which is what we want with a 95% confidence interval. Our sample standard deviation is 11.3, and our sample size is 150. So if we plug this into our formula, we get a margin of error of 1.81. To calculate our 95% confidence interval, we then take our sample mean of 120 and then add and subtract our margin of error of 1.81. And this gives us a 95% confidence interval of 118.19 to 121.81. And our interpretation is that we are 95% confident that this interval actually contains the true population mean IQ score among college students. So let's try another example problem. Suppose that 160 nurses took a job performance test. From the data, you find that the sample mean equals 80 and the sample standard deviation equals 15. What is the margin of error associated with a 95% confidence interval? What is the 95% confidence interval? What sample size is needed for our 95% confidence interval to have a margin of error no larger than 1.5? And what is a 90% confidence interval? Interpret. So as you can see on the bottom of the slide, the formulas for the 95% confidence interval and 90% confidence interval are almost exactly the same. The only thing that's different between these is the significance level, or alpha, which affects the t-score used in our equation, as we'll see. Again, because our sample size is large, the t-distribution approximates a normal distribution, and our t-value is 1.96. Our standard deviation is 15 and our sample size is 160. So we again plug this into our formula to get a margin of error of 2.32. We then take our sample mean of 80 and then add and subtract our margin of error from this value. And this gives us a 95% confidence interval of 77.68 to 82.32. And we interpret this as we are 95% confident that this interval actually contains the true population mean performance test score among nurses. And as we discussed earlier, increasing our sample size is the best way to decrease our margin of error, which we would like to do because this increases our confidence that our sample estimate is close to the true value. The third question asked was, what sample size is needed for our 95% confidence interval to have a margin of error no larger than 1.5? To answer this question, we simply rearrange the margin of error formula and instead solve for the sample size. One thing to note here is that our t-value in this formula is replaced with z. And this is because t-values are dependent on sample size, but we're trying to solve for that here. So because we're interested in calculating a 95% confidence interval, this would be 1.96. We plug this value into our formula, as well as our sample standard deviation and our desired margin of error, and we get an answer of 384.16. But we can't have a sample with 0.16 of a person, so we always round this answer up, and this gives us 385. And our interpretation is that we need a sample size of 385 in order to have a margin of error no larger than 1.5. Part D of the question asked us to calculate and interpret a 90% confidence interval. 95% confidence intervals are the most common, but you can calculate a confidence interval for any level of confidence. With a 90% confidence interval, our formula will be exactly the same as with a 95% confidence interval, except for our significance level, which now equals 5% rather than 2.5%. So if we look at our t-table, we'll see that the t-value associated with 5% in each tail with a large sample size is 1.645. So we plug this information into our formula to get our margin of error. We then add and subtract this margin of error from our sample mean of 80 to calculate our confidence interval of 78.04 to 81.96. And we conclude that we are 90% confident that this interval actually contains the true population mean performance test score among nurses. Usually when people talk about confidence intervals, they're referring to two-sided confidence intervals, which we've just calculated. But sometimes you're only interested in determining an upper bound for a population mean or a lower bound. And this is what we call a one-sided confidence interval. The major difference is that we do not divide our alpha by 2 in calculating our margin of error like we did with a two-sided confidence interval. So if we're interested in a 95% one-sided confidence interval, we would just use our alpha of 5%. Whereas with a two-sided 95% confidence interval, our alpha is 2.5%. We then add this margin of error to our sample mean for an upper bound, or we subtract this from our sample mean for a lower bound. Let's turn to an example. You obtain a random and independent sample of exam scores of 25 students, and you calculate a sample mean of 82 and a sample standard deviation of 5. Construct and interpret a one-sided 95% confidence interval and obtain the upper bound for the true population mean. So as I mentioned, our alpha level here is equal to 5% in the tail rather than 2.5%, which we would use if we were calculating a two-sided 95% confidence interval. Since our sample size is quite small, we look up our t-value. And we see that with a degrees of freedom of 24, based on our sample size of 25, and a 5% alpha, we get a t-value of 1.71. We then use our confidence interval formula and plug in our t-value of 1.71 and other relevant values, and this gives us a one-sided confidence interval of 83.71. So we conclude that we are 95% confident that the true population mean is less than 84.06. So now I just want to connect the dots with some of the concepts that we've talked about so far. So first, the sampling distribution of the sample mean. The idea of repeatedly sampling a population, each time calculating a mean, and how these sample means will approximately follow a normal distribution centering around the true mean. We know that 95% of the sample means will be within plus or minus 1.96 standard deviations of the true mean. If we know the true mean and standard deviation of our population, we can calculate a confidence interval that will tell us that we are 95% confident that we will get a sample mean that is within our calculated interval. So in this case, the confidence interval is focused on the sample mean rather than the true mean because we already know the value of the true mean. Our confidence interval formula includes our z-score and the standard deviation of the sample mean. The standard deviation of the sample mean tells us how far sample means vary from the true mean on average. It's also possible that we have a situation where we know the population standard deviation, but not the population mean. In this case, our formula for the confidence interval is exactly the same as the first formula, except that we substitute the sample mean for the true mean. But this situation is extremely rare. If we don't know the true population mean, then we probably don't know the true standard deviation. And our interpretation of a 95% confidence interval in this case would be we are 95% confident that the confidence interval will capture the true mean. So let's say we select only one sample, which is most often the case. In this situation, we would only have the information available to us in our sample, so we wouldn't know the true mean or the true standard deviation. In our confidence interval formula here, we use a t-score, which accounts for the extra uncertainty in not knowing the true standard deviation. And we also use our standard error, which is an estimate of how close our sample mean is to the population mean. Multiplied together, this t-score and standard error are known as the margin of error. And the margin of error tells us the maximum expected difference between the true population mean and the sample estimate of that mean. And when you calculate a 95% confidence interval in this situation, the interpretation is we are 95% confident that the confidence interval will capture the true mean. In our next tutorial, we'll introduce hypothesis testing and discuss types of errors and statistical power.